Welcome guys back to another video on fluid mechanics. I'm going to be solving a particular question also here on fluid mechanics. So now if you guys watched my previous video in which I proved a particular expression on how to calculate pressure of atmospheric or pressure of an atmosphere due to a certain height, blah blah blah, due to adiabatic process. Now you should be able to know that we are solving a particular question on also using that expression we proved to calculate it. Now if you look at this particular question, it says the pressure and temperature of air at sea level is 101 kilonewton per meter square and 288 Kelvin. Respectively, determine the pressure, density, and temperature at an altitude of 9 km, assuming a polytropic atmosphere for which pressure divided by the density raised to power 1.235 is a constant. Another question also said, what lapse rate does it represent? Take the specific gas constant for air as 287 joule per kilogram per Kelvin, and this here equals constant. So now I'm just going to explain what is all talking about. So solution. Now the solution to solving basically all this long question is to write out the parameters. So we're having pressure and temperature of air at sea level, which is this and this. So let's call it my initial temperature. Basically, if you remember, watch my last video. At sea level can be a ground level or basically a standard point for starting measurement. So taking it up to a particular height, you can have your initial pressure at this point. You can have your initial density at this point, then you can have your final pressure, and you can have your final density. You can have your initial temperature at this point, you can have your final temperature at this point after a certain height. So the height given here is what? 9 kilometers. So I've just basically explained what this question is talking about. So basically it says the initial pressure and temperature here at sea level is this. Now you're asked to find your pressure and density and temperature here at this height, 9 kilometers. Very simple. So now first let's write out our parameters. So writing out the parameters, we have my initial pressure, which is what? 101 kilonewton per meter square, right? I just can basically write this as 101 times 10 raised to power 3 newton per meter square, right? Now I can have they gave me my initial temperature, which is T naught equals 288 Kelvin, right? Now they gave me my altitude, which I can represent as H, 9 kilometer, right? Now what else were we given? Now from this, if you can remember, a polytropic process or a polytropic expression is always written as P, or an adiabatic expression is written as density raised to power n equals constant, right? Where n can be a polytropic constant or an adiabatic constant. If it's an adiabatic constant, n will be 1.4. So if it's not 1.4, it's a polytropic process. So since it's a polytropic process here, and the n given here is what? If I compare this with this is P raised to power density raised to power 1.235 equals my constant. So the n given to me there is 1.235. So my polytropic constant is what? 1.235, right? So what else were we given? Now we are given my specific gas constant, which is represented as R, which is what? 287 joule per kilogram per Kelvin, right? So I've written out all my parameters. Now remember the question says we should calculate my pressure at the height. Let's represent it as P, which is unknown, density at the height, which is unknown, and pressure at this height is also unknown. So I'm looking for this, and this. So how do I find this? First, let's go with pressure. The pressure at a particular point in atmospheric pressure, or the particular point in air, due to a polytropic process or an adiabatic process, is always given as P is equals to my initial pressure, open bracket, 1 minus n minus 1 over n times G divided by RT naught raised to power n divided by n minus 1. So Now if you watch my previous video, I actually prove this expression. So now this is what we are going to be using to solve this particular question. So they asked us to find my pressure at this height. They gave me my initial pressure, initial density, and initial temperature. So now let's solve. So my initial pressure here they gave me is what? 101 times 10 raised to the power 3, open brackets, 1 minus my n, my polytropic constant, which is given as what? 1 minus 235 minus 1 divided by 1 minus 1.235, right? Then times my gravitational constant, don't forget my g is what? 9.81. So this is 9.81 times my height given is what? 9 kilometer, which can also be written as 9,000 meters, which is 9,000 divided by my specific gas constant, which is what? 287, right? Then what else? Then my initial temperature, which is 288 Kelvin. This is 288 Kelvin. Close my bracket, raised to power my adiabatic constant, which is what? 1.2, sorry, my polytropic constant, which is 1.235 divided by 1.235 minus 1. Just calculating my pressure. Imagine, just for calculating my pressure, I just need all this. So now let's calculate. So now I can basically just simplify my inner expression here. So simplifying this inner expression, I have 1 minus 0 2 points, that's 0.20325. Close my bracket, raised to power 1.235 minus divided by 1.235 minus 1. 101 times 10 raised to power 3 equals P. So 1 minus this, I have 0.7967 raised to power 1.235 divided by 1.235 minus 1, then equals 101 times 10 raised to power 3 equals P, right? So 1.235 divided by 1.235 minus 1, then simplifying this 0.7967 raised to power, this expression here definitely have 101 times 10 raised to power 3 times 0.3023, yeah, 0.3030. Let's put it like that. So multiplying this by this, we have 30600.41. Don't forget the unit of pressure is what? Newton per meter square. So you can just basically leave it as kilonewton. That's dividing by 1000. We have 30.600 kilonewton per meter square. So now I've gotten the pressure at the height of 9,000 meter or 9 kilometer. So our next step is calculating. Let's first calculate my temperature. So calculating the temperature, what do we do? So the formula for calculating the temperature at a particular height in atmosphere is very similar to the one for calculating pressure. The one for calculating temperature is T is equal to the initial temperature, open bracket, 1 minus n minus 1 over n, close bracket, GH divided by RT naught. So now this is just exactly writing the one for, if you can just see the similarities between the two expressions, it's just basically writing this inner one and writing this inner one, but replacing it with my temperature, replacing my temperature, but not including n divided by n minus 1. As simple as that. So you can basically cram that and put it in your workbook. So now let's calculate. They said we should calculate my temperature at the height of 9,000 kilometers. So they basically gave me my initial temperature here, which is 288 Kelvin, and they gave me my polytropic constant, which is n is equals to 1.235, and they gave me my gas constant, which is 287 joule per kilogram per Kelvin. And what else did they give me? And they gave me my height, which is 9,000 kilometers, sorry, 9 kilometer or 9,000 meter. And what else? So that's that. So now we can just basically substitute and get our value. So substituting this into this expression, we have to write my initial temperature, which is giving me as 288, right? Open bracket. 1 minus my n is what? 1.235 minus 1 divided by 1.235 times my gravitational constant, which is 9.81 times my height, which is 9,000 meters, divided by my r, which is 287, times my initial temperature, which is what? 288. Close the bracket. So back to simplification. Simplifying this, we have 288 open bracket 1 minus, simplifying this, we have 0.2033 close bracket. So 1 minus this times 288 will definitely give me 0.7967. So times 288 equals my temperature. So this times this gives me 229.45 Kelvin. So this is the temperature at the height of 9 kilometers. So now what's left is to calculate my density. So to calculate my density, we know that from my equation of state, we said pressure divided by density is equal to R times my temperature. So this is what is called an equation of state. So basically this was gotten from pressure times specific volume equals RT. So specific volume, which is the inverse of density, give me this. So using this particular expression, I can easily calculate my density. So given the pressure at a height of 9,000 kilometers, which we got as 30.6 kilonewton, 30.600 kilonewton, or just basically kilonewton per meter square, or 30,600.41 newton per meter square. Then the temperature we got at 9,000 meters was T, which is equal to 229.45 Kelvin, and my specific gas constant, which was given as 287 joule per kilogram per Kelvin. So substituting this, we can easily get my density. So the density at 9,000 kilometers will definitely give me, making density subject to formula here, we have density is equal to pressure divided by RT. So this gives me my pressure, which is what? 3600.41 divided by 287 times 229.45. So this gives me my density at the height of 9,000 meters, gives me 0.465 kilogram per meter cube. So that's my density. So now remember we were given two questions. The second one says, what lapse rate does this represent? So basically the formula for calculating lapse rate is basically defined as the change in temperature due to change in height. So going up at a certain height, there will be a change in temperature from this to this. So that is basically the lapse rate. So change in temperature divided by change in height. So that's just exactly what lapse rate is. Lapse rate, which is presented as L, is equal to change in temperature due to change in height, right? So this basically is equal to minus G divided by R, open bracket, n minus 1 over n, close bracket. So this is a very simple formula for calculating lapse rate. So basically we are just going to input our parameters, since we are given G, which is 9.81, and R, which is 287 joule per kilogram Kelvin. Then we are given my N, which is my adiabatic constant, which is 1.235. Then we can easily get my lapse rate. So L is equal to minus 9.81 divided by 287, open bracket, n 1.235 minus 1 divided by 1.235. So simplifying that, my lapse rate is equal to Kelvin per meter. So my lapse rate here will be negative since my n is greater than 1, and since it's greater than 1, then my temperature decreases with increase in height. So thank you guys for watching. Please and please subscribe.